So the last thing that we're going to look
Alex
at
is here. Sorry.
thank you, is on vectors. And is anyone studying vectors or know what vectors are? I think so.
I know them in medicine. I don't know them in.
Okay, yeah. In engineering or physics or
It's a line.
Oh yeah, that's right.
Right?
yeah.
From two.
Yep.
Isn't a vector an arrow that goes off in the direction?
Yeah, it's like an arrow. Yep. Has a start and a stop point, so it doesn't necessarily go on forever, but it is an arrow. Yep. So the idea of a vector is it's used to model or represent something that has both a magnitude and a direction to it. Okay, so an example of that is a velocity. To describe the velocity of something, that's not the same as describing the speed. Okay, velocity means you're describing the speed and the direction of that speed. Okay, so that's what a vector is. It represents, in one type of situation, how fast something is going and the direction it's going. Another example of a vector you could use is a force vector. In that case, it doesn't measure how fast something is going, but it measures how strong a force is, like how hard you're pushing or pulling on something, and then the direction that you're pushing or pulling. Okay? So the direction part is always pretty consistent, but the magnitude part can be different. If it's velocity, magnitude is speed. If it's force, then the magnitude, I don't know, in physics, I think you use newtons to represent force. Okay? And one example you can think of for vectors would be like air traffic. If you had all kinds of different airplanes flying, every plane has a speed and a direction to it. And it's the job of the airport and air traffic control to make sure all those different planes are spaced out enough and safe enough, different altitudes. So you could think of all those airplanes as vectors that have to be managed by people and computers. And there's hundreds, thousands, at one time they're trying to keep track of. So one way we can represent a vector is using a ray, okay, or like an arrow. I'm going to change that to arrow because ray implies that it goes on forever. It doesn't. It stops. And so does an arrow. An arrow can have a stopping point. So the direction that the arrow points, that's the direction of that your object is traveling or that you're pushing or pulling. But how do you think you would represent magnitude with an arrow? Yep.
How long the arrow is?
Yep. How long the arrow is. So the length of the arrow represents the magnitude, and the way that it points is the direction. So if these were two objects traveling, both objects are traveling in exactly the same direction. But what would be the difference between the two?
Long arrow has greater magnitude.
And if we're talking about velocity, that would mean that object is
Faster.
going faster. Yep. If those represented forces, like maybe wind blowing to the right, the bottom one would represent a stronger wind, more force. So generally when we describe a vector, it has a starting point and a stopping point. So let's say we have the vector starting at P and ending at Q. Okay, let me draw that. Here's P, here's Q, capital Q. That would be the vector PQ. Doesn't have to be. I just made that one up. Okay, but P is called the initial point. Q is called the terminal. Terminal is where it ends. Now, how do we name a vector? Well, we can name a vector using a single letter. But the problem is in math, what do you use single letters for? Use them for variables. So we can't just use a single letter to name a vector because we might think it's a variable. Variables and vectors aren't the same thing. So what you can do to your single letter is one of two things. To indicate that this means vector m, not variable m, you can put a little arrow on top of it. Or you can make the letter bold. That's what you're going to see most of the time. Okay, the letter is going to look bold. Also, I'm not sure if I mentioned it yet, but the homework for tonight, it's in a different book. So it's still a PDF, just like you're used to. It's just when you open the PDF, it's going to look different because it's not exactly the same layout. But there's still problems and they're numbered. Just a different book. Okay, so letter with an arrow on top, or make the letter bold. Okay, and our book does bold most of the time. That's what they use. So let's look at what happens when we add two vectors together. Let's say that you had, let's pretend that this is like wind, okay, like a fan. You had a fan that's blowing up, and you have another fan that's blowing to the right. And let's say you aim, both those fans on an object, kind of like that. Let's say maybe you had like a little pool or something, and you have something floating on it, like a little sailboat. If you aim a fan to the right and a fan pointing up on the sailboat, what's going to happen to the boat?
It will start to upright.
Right, the boat's going to start to move in the direction that it's being blown. It's being blown in two directions. It's going to move up and to the right. It's actually going to move exactly like this. And I'm going to explain what I'm doing, but I think you'll probably understand the idea. That is exactly how the boat's going to move. That vector that I just drew in green. What I did by taking these two vectors and stacking them together like that and drawing in the diagonal, that's called adding two vectors. It's not doing it numerically, it's visual, but that is how you add two vectors together. The point that I tried to make by drawing that is when you add two vectors together, the answer is a new vector. Notice it's a different length than both of the originals, and it's a different direction. So when you combine two vectors together, you can get a new vector that points a different way and can be a different length. Depends on the two vectors you combine together to get the new one. And the way that you add two vectors together is you position them. Let's call the red one V, and let's call the black one W. If you want to add V and W together, you want to line them up so that the ending point of V, which is right there, that's the ending point of V, and the starting point of W, which is right there, line up. So you position them just like that. So the ending point of V and the starting point of W line up. You can only connect an end to a start. You think of them like Legos. They can only connect a certain way. If you put the sides of Legos that both have the bumps on them together, they don't connect. One side has to have the bumps, and the other side it plugs into the bumps. So you can only connect an end to a start. You can't do this. That's an end to an end. That doesn't work. End to start. Once you connect them, the answer is found by connecting the starting point of the first vector to the ending point of the second vector. Just like that. So drawing them out is a real good way to visualize what's going to happen when you combine two vectors together.
Question.
Mhm.
Why is the green one pointing towards the terminal side, pointing towards the terminal side? Wouldn't that be swapped around?
Well, W is up,
Yeah.
V is right,
Yeah.
so green is up and to the right.
Okay.
If you swap it around, then green would be pointing down and to the left, but neither of the original vectors would give you any kind of downward motion or left motion, because the original ones are right and up.
So despite that, the terminal side, terminal point of the green vector still matches up with the terminal point of W vector.
Yeah, that's just when you draw your final answer. Yeah, that's how you have to draw your final answer. Final answer is always beginning to end. And you can do it with as many vectors as you have. So let's say you had one that went like this, one that went like this, one that goes like this, and then one that goes like that. If you want to know what would happen if you combine all four of those together, you can take this one, put that one, put that one, and then put that one. And the final answer would be connecting where you started to where you finished. That's the result if you combine all four of those vectors together. And the order you combine them in, it doesn't matter. So I did black, red, green, blue. Let me do them in a different order. Let's do green, and then let's put green here. Let's put black there. Let's put red. And then let's do blue. Order shouldn't make a difference. I should still be able to connect where I started to where I stopped, and I should get exactly the same answer. Yep. Any question on that? What's that called when you can add things up in a different order and you still get the same answer? Remember the name of that? Begins with a C.
Corresponding.
No, not corresponding. It's a good guess.
It's not constant.
No, not constant. It's kind of like if somebody drives back and forth to work every day. What do you call that? That's their commute. Commutative property. Yeah. So you get the order that you add them in. You can change the order around, and you still get the same answer. Yep, commutative. All right. Do I have another example? Yeah, let's do this one first. Okay, let's add V and W together. So here's V, and then I'm going to position W so that the end of V and the beginning of W are right at the same spot. And then how do I get my final answer?
I draw from the start point to the end point.
Start point of
V,
V
the end point of W.
to the end point of W, just like that. So the answer to this problem is it's an image. You actually sketch your answer.
Are we using calculators today?
No, I don't think we'll need any calculators. Depends how far we get into part 2 if I start it. Then we will. But we'll see. Okay. What do you think is going to happen in example 2? Well, you got to connect the end of V to the beginning of W. So you have to line up those red dots. And then once they're lined up, you're going to connect the start to the finish. So you have to line the red dots up, and then after you do that, connect the green dots. So let's just group these together. So if it wasn't perfectly like horizontal, you'd do something like this. You'd line the red dots up, and then you'd connect the first green dot to the second green dot. But they're perfectly horizontal, and they're the same length. So when I line up the red dots,
0 or 1.
the green dots also line up. So what did we say? When you add two vectors together, you always get a what?
A new vector.
You get a new vector. So the answer here is a vector, but it's what we call the zero vector. So it's a bold zero. Or you could make it a zero with a line on top. So the zero vector, that's kind of a special case. It's the only vector that doesn't have magnitude, and it doesn't have a direction. So it's kind of its special case. Any question on that? All right, I already told you this, so I'm not gonna go through it again. But vector addition is both commutative and associative. Commutative means you can change the order you stack the vectors up in, and you get the same answer. And I already showed you that. And it works for as many vectors as you have. You can do it with 2, 3, 20. As long as you stack them all together the right way, you're still going to get the same answer. Just think about adding numbers up. You can add numbers up in any order you want, you get the same answer. Now, associative, that doesn't have to do with the order you add things up in. That has to do more with grouping. You can group things differently and you still get the same answer. Okay, that's associative. It's like doing different order of operations. Okay? And when you're adding vectors together, whether you add a plus b first and then do c, or do b plus c first and put that on the end of a, you'll get the same thing. Okay, I didn't show you this one, so I'll do this one real quick. All right, let's take these three vectors and just repositioning one of them a little bit. Okay. So let's do it the way it says on the left. On the left, what does it say to do first?
A plus B.
Okay, so let's do A plus B. And I'm just going to draw that by hand. Close enough. Okay, so that's A plus B. Then what does it say to put on the end of that?
Plus C.
Plus C. So I'm going to take, I just don't want C to line up perfectly with that. That's why I was trying to adjust it. All right, let's put C like this. Okay. So now let's put C on the end. So we got that. Final answer looks kind of like that. Okay, so that's what you get if you do it the way it's on the left. All right, now the way that's on the right. What does it say to do first there?
B plus C.
Okay, so let's take B plus C. Okay, take and draw that. Okay, so I don't need those anymore. Okay, so there's B plus C. And that's going to go on the end of what? A. It's going to go on the end of A. So let's take A, do B plus C. And again, I didn't really measure it, but if I did it somewhat carefully, these two green vectors should look pretty close. Yeah, not bad. Pretty close. Right. But they should be exactly the same. So the order that you add vectors up in, as far as the commutative property doesn't matter, and then putting parentheses and doing something first and something second, that doesn't make a difference either. Okay, what I'm mentioning here, V and negative V, we just did an example of something like that. This would be an example of V, and I called it W, but it's really negative V. The only thing that a negative does with a vector is it makes it point the other way. That's what a negative does. It's like it rotates at 180 degrees. And when you add two vectors that are opposites,
It's 0.
you get the 0 vector. Yep. You don't get 0 the number, you get 0 vector. Essentially, the 0 vector means that everything is balanced. It's like a tug of war, and however hard one team is pulling, the other team's pulling exactly as hard in the opposite direction. So essentially nothing happens. There's no movement at all.
So now what happened at the pep rally when we crushed the teachers?
Oh, is that what happened? Yeah, so no, then that's not the 0 vector. One side had more force than the other. So the difference between v and negative v is just the direction they point. How about their magnitudes? What's the difference between v and negative v?
They're the same.
They're what?
They're the same.
Yeah, they're exactly the same. So the difference between v and negative v is they point in opposite directions, but they have the same magnitude. All right, now, we know how to add two vectors together. I want to look at how to subtract. We basically do it like addition. What if I gave you this problem, and you didn't know how to do subtraction, but you knew addition? How can you rewrite 5 minus 2 as an addition problem? That'll give you the same answer. Yeah?
Just 5 plus negative 2?
Right. 5 plus the opposite of the second number. If you add the opposite of a number, you're really doing subtraction. And that's exactly how you subtract two vectors. Instead of trying to think of like a new method to do it, we don't do anything new when we subtract. We're going to add the opposite of the second vector. And we just talked about what the opposite means with a vector. What does it mean when you put a negative in front of a vector?
It points in the opposite direction.
It just points the other way. So if instead of doing subtracting, just add the vector that points the other way, and that's subtraction. So subtract, find the opposite of the second vector, make it point the other way, and then add it just like you normally would. All right, so we're going to try subtracting two vectors in a second. Okay, so I want to do v minus w. First, can somebody tell me how I'm going to think of that so it's not subtraction?
V plus negative W.
Right. We're going to think of that as v plus negative w. Well, we've got v. We've got w. What do I need to find first so I can do the subtraction?
Negative W.
I need negative w. Yep. And remember, negative w is the same vector. It just points the other way. There you go. So there's negative w. So now, to do v minus w, think of it as v, and then add negative w. And then draw your diagonal. That's how you do v minus w. So about like that. So subtraction isn't really any more complicated than addition. Just remember to flip the second one before you add it. Any questions on that? Okay. What do you think would happen if I did this? So let's say I had a vector w, and then I wrote down the vector 3w. What do you think the 3 in front would do? Yeah?
It would triple the magnitude.
Yeah, it would triple the magnitude. How about the direction?
It'd keep the direction the same.
Yeah, keep the direction exactly the same. When you make something bigger, or you could also make something smaller, that's called scaling, right? Scaling. When you make something bigger or smaller. So when you put a number in front of a vector, that is called a scalar product. And the idea, when you put a number in front, you get a new vector. Okay. If you put a number bigger than 1, it's going to give you a longer vector than you started with. If you put a number between 0 and 1, like 0.5, 0.6, 1/3, it's going to give you a shorter vector. What's going to happen if you put a negative number in front?
Kind of flip it.
It's going to flip it, exactly. So there's 3 things that can happen when you scale a vector. It can get longer, it can get shorter, or if you put a negative in front, it can also reverse the direction of it. Okay, but it gives you a new vector. That's what's important. Longer, shorter, or flipped. That's all that can happen. So let's try an example now. So here's the vector v, and they want me to find 2v. Okay. How could I get 2v without measuring or using a ruler? Just using the smartboard.
Copy and paste it with the same image.
Yeah, just copy and paste 2 of them together. That's 2v. So here's v. Put another one with it. Oops. Copy. Where is it? Might be cloning it right below the screen. Oh, it was. Okay. I don't need that one. Just put that up there. Okay. So there's 2v. And then just draw your final answer. Where you started to where you finished. So 2v is exactly twice as long, pointing in the same direction. How about 1/2 v? How's that going to compare to v?
It's really smaller.
How much smaller?
Half as long.
Yeah, it's going to be half as long. I don't have a way to really estimate exactly half or calculate it on the smartboard, so I'm just going to estimate where I think halfway is. Maybe about like that. Of course, if you have graph paper, then it's easier to get an exact answer.
How are we gonna do this on the homework?
Some of it will be matching, some of it will just be you will have to draw it. And they'll give you like a grid, and you can draw it. You can grab graph paper if you want, or use your own. Yeah. All right, let's try this one. Negative 1v. That's the same as just negative v. How would I sketch negative v? Yeah.
Just change the direction, keep it the same.
Same what?
Length. And
Yep.
Just change the direction of it.
Keep the magnitude the same and just change the direction. So there's negative v. How about negative 1/3 v? What would I have to do for that?
Change the direction again, but only go a third way.
Yes, I already got the direction changed, so I'll just stick with that one. And just estimate where you think about 1/3 might be. Okay, so that's negative 1/3 v.
No.
Any question on that? All right, we can try this one. This is kind of the same as what we did before, but it's adding vectors and scaling them at the same time. Okay. So what are they asking us to find first here?
2v.
2v. So we can do that first. All right. There's 2v. And then what are we adding on the end of 2v?
3v. I mean w.
3w. So just make 3 copies of that. So the one thing about graphing is you kind of have to think ahead a little bit and make sure you don't go off the edge of your graph paper. So I knew all these vectors were going to the right. So I wanted to start way on the left. Okay. That's one thing you got to think about a little. All right. And so now I got 2v, I got 3w. What's my final answer? How do I get
Go
that?
from your initial V to your final W.
Yep. So start at V, go to W, and that is your final answer. Any question on it?
No.
All right. So that's adding and scaling at the same time. So we've talked about 2 things with vectors. We say they have a direction and they have a magnitude. Well, there's a symbol for magnitude. When you see a bold letter, that's a vector. And when they put double lines around it, double lines mean magnitude. So magnitude is measuring how long the arrow is. So what kind of number do you think magnitude always has to be? It's measuring how long something is.
What's positive?
Yeah, it always has to be a positive number. Yep. Magnitude is always positive. And I'll give you kind of a hint at how we are going to find the magnitude. Actually, you'll probably be able to figure it out. If you had a piece of graph paper, you had, let's draw in a nice straight vector like that. How do you think you would figure out how long that is?
Rise and run.
Okay, so what would you do if you figured out like the rise and the run?
No. Whatever that equation is, that MX slope or whatever.
Well, we're not finding the slope. I want to know how long that is. You could use the distance formula. Yep. If you know this coordinate and this coordinate. And the distance formula is really just the Pythagorean theorem. If you just count 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, that's why when you said rise and run, those are the 2 numbers you need. But then the theorem you use is Pythagorean theorem, and you have the magnitude. So finding the magnitude is really pretty straightforward. Sweet. So what would be the difference between the magnitude of vector x and the magnitude of the vector negative x?
Absolutely nothing.
There wouldn't be any difference at all.
Gosh, why are you using double?
That's just the symbol.
Okay.
That's what our book uses.
Okay.
Yep. I don't know if other books might use something different, but that's
This
what ours
wouldn't
is.
let
That's just for vectors.
Yeah, I've never seen it anywhere else. So the magnitude of x and the magnitude of negative x are exactly the same thing. Now you might think, wait, they're pointing in opposite directions, but that's not what it's asking. It's asking how long are they? Well, the first one is like measuring the distance from where I am to the door, and the second one is from the door to where I am. It's just a different direction, but it's the same magnitude. Now, if the magnitude comes out to exactly 1, there's a name for that. Does anyone remember when we talked about circles? We did a lot with a circle that had a radius of 1, and we called it a blank circle.
Unit circle?
We called it a unit circle.
Is a unit vector.
When you have a vector that's exactly 1 unit, That's called a unit vector. Yeah. It's called a unit vector. And we're going to talk more about unit vectors, maybe a little bit today, definitely more tomorrow. A unit vector is just a vector with a length of 1. Now, sketching vectors is great. I think it's fine, but it's not the fastest way to do things. If you have a word problem, then yes, it's probably very helpful because you can kind of see what you're doing. But if you just want to add 2 vectors together, I'd rather you just give me numbers that I can just add real quick and not have to draw it. So I'm going to show you 2 other ways that you can add vectors together without drawing arrows. And the first way I'm going to show you is what our book calls an algebraic vector. And it's not very complicated. An algebraic vector would look something like this. That's an example of a vector that's all numbers, no arrow. Anyone have an idea what the 5 and the 8 mean?
5 vector, 8 vector. Total. 5 units and 8 units.
5 units which way?
To the left. To the right.
To the right. And then
8 units up.
and 8 units up. Yeah. That's basically what that's telling you. So the A and the B are like a horizontal and a vertical. You can think of the A and the B as like directions. In the case of the one I wrote, 5 units right, 8 units up. We call the A and the B the components of the vector. The horizontal and the vertical components. So if I go back to that one where I showed you how to find the magnitude with the Pythagorean theorem, the 4 would be called the horizontal component, and the 7 would be called the vertical. So you could actually write that vector as the vector 4, 7.
Now, quick question, because 7 is the magnitude.
7 is the vertical component.
Yeah, so what if it was like -4, -7? So obviously you'd go 4 to the left, but it goes down 7? Or
Yeah, so -4, -7 would mean like start here, 1, 2, 3, 4, and then 1, 2, 3, 4,
Yeah,
5,
I
6.
said, obviously it's the same thing, but
It's the same magnitude,
same magnitude.
but opposite direction.
So like for these ones you can sketch it if they're negatives.
Yeah, yep. Negatives just mean to go left and down. Positives mean right and up.
Yeah.
Yep.
Oh wait, I was getting too confused.
So the A and the B are what we call the horizontal and the vertical components. So essentially, A tells you to go left or right. B tells you up or down. So A is all about left or right. B, up or down. But there is something that this notation doesn't tell you. Like when I write something like this and say 3, 2, it tells me to go 3 right and it tells me to go 2 up. But what doesn't it tell me? Yeah?
Your starting point.
It doesn't tell me a starting point. And that's because the starting point can be anywhere. It doesn't matter where you draw it. Okay, so like if I was going to draw the vector, let me just see what else I have before I do that. Yeah, if I was going to draw the vector 3, 2, let's use that as an example. Okay, let me zoom out a little bit. Okay, 3, 2 could be drawn like this. 3, 2 could be drawn like this. 3, 2. Put it over here. 3, 2. You put it anywhere you want. Those are all the vector 3, 2. There is a place that's most common to start from. Where do you think the most common place?
The origin.
Yeah. The most common place to start from is the origin. And if you start from there, the vector has a special name. It's called a position vector. So if a vector has its initial point at the origin, that is a position vector. So let's see how we could take one of these and figure out, like if they didn't give you a picture, that it's the vector 3, 2. So let's say they gave you this one in the upper right. Let's write the coordinates of the start point and the stop point. What's the coordinates of where that vector starts?
5, 1.
5, 1. And how about where it stops?
8, 3.
8, 3. So now, if I just gave you those two pieces of information, starts at 5, 1, stops at 8, 3. Anybody figure out a way that they could get the vector 3, 2 somehow from those two coordinates?
X2 minus X1 and Y2 minus Y1.
Yeah. If you take the ending point and subtract the starting point, you will get the position vector. That's how you do it. And you have to do that for the x's and the y's. 8 minus 5, there's your 3. 3 minus 1, there's your 2. And I'm going to write that down. So that's the formula to find a position vector. Okay, so to find a position vector, if the initial point is not at the origin, if it's at the origin, it's already done. If it's not, well, then they have to give you 2 points. And they do have to tell you which one is which, because it makes a difference the order you subtract. You have to do terminal minus initial. If you switch it around, what will happen to your vector? Like if you don't do terminal minus initial, you do it the other way.
It'll be negative.
Yeah, you get the negative of your vector. It would point the wrong way. That makes a difference. So it's always the terminal minus the initial, and then terminal minus the initial. Okay, so any question on that formula? That's called the position, that's the formula to find a position vector. All right, well, let's try. So generally, if they ask you to find a position vector, they're not going to give you a picture. So you're not going to be able to just count how many right, how many up. You're really going to use that formula to figure it out. It's kind of like figuring out the rise and the run. That's what you're really doing. You're finding the rise and then the run. Okay, so let's find the position vector between these 2 points. Can someone tell me my calculation to get the horizontal component of the position vector?
4 minus negative 1.
4 minus negative 1.
Plus.
Sorry, yeah, it would be 4 plus 1. And what about the vertical component?
6 minus 2.
6 minus 2 has to be in that order. So what's your final answer going to be?
It's going to be 5, 4.
5, 4. Yep. That's the vector that would start at the origin, and it would go right 5 and up 4. And that would be the position vector for those points, if you started it at the origin. question on that? Okay. All right, so I've shown you guys two ways that we can represent vectors. The first way I showed you was to draw it with an arrow. Second way I showed you, what was the name that I used?
Numerically.
Well, it had numbers in it, but what was the name of that?
Like position vector.
It was before that in the notes.
Algebraic.
Yep, it's called an algebraic vector. And the last way I'm going to show you is called unit vector notation. This is the most popular way to write vectors, okay, unit vector notation. Nothing wrong with the first two, they're fine. But this is just the one that's used the most. Now, what did we say about unit vectors? What's special about them?
They have a magnitude of 1.
They have a magnitude of 1. Yep. So we're going to look at two special unit vectors. The first special one is called I. Has nothing to do with an imaginary I, it's just the vector I. I is a special name with vectors. So if you want to pick a name for a vector, don't ever pick an I. You can't pick I. I is something special. I is simply a vector that's 1 unit long, and it points to the right. There's a picture of what I looks like. It looks just like that. It's 1 unit long, and it points to the right. And there's one other special vector. It has a name. Anybody have a guess what we're going to name that one? Based on the first one being I?
J.
J. Yeah. So J is a vector that's 1 unit long, and it points up. So if you're doing a word problem and you need to pick a name for a vector, do not pick an I and do not pick a J. You also shouldn't pick K. We haven't talked about that yet. That's 3D. So you can pick any letter other than I, J, or K. I might not use the letter O. It could look like a 0. But technically, anything other than an I, J, or K is fine. Okay, and J looks like this. It's 1 unit long, and it points up. So the idea of unit vector notation is you are stacking I's and J's together to build your vector. So think of I and J as building blocks, okay? And we're going to stack them together. Okay? And I'll show you how we stack I's and J's together to build a vector. So remember, I points right, J points up. Okay, let's build the vector 3, 4 using unit vectors. Doesn't matter where you start. We're just going to go from the starting point over 3 to the
Right.
To the right. 1, 2, 3, 4. 1, 2, 3, 4. So now let's build that vector stacking together I's and J's. Okay. Here's I. How many of those I's would I need to stack together starting here to get me lined up with the terminal point? Yep, I'm going to need 3 of them. So I'll make 3 copies of that. So there's 1, 2, close enough, and oops. 3. Okay, so there's 3 of those I's stacked together. And what do you think you would call that vector on the bottom now?
3i.
Yes. 3i plus, we have to add something on the end of it. Yeah, I'm not going to copy and paste. I'm just going to draw. 1, 2, 3j, 4j. So we would call that one, what did we say? 4j. That is unit vector notation. It's very similar to doing what we did before, except instead of putting angle brackets and putting the two numbers with a comma, you just do 3 of the i's plus 4 of the j's. So it's the same two numbers, just written a little different. Okay, any question on that? What if you wanted to do something like this, though? Start here and go that way. How many i's would you need?
3.
Yep, you need 3 i's. 1, 2, 3. But how many j's would you need?
You have 2.
2.
Negative 2. Has to go down 2. So that's 3i minus 2j. And then if you connect the start to the finish, that's exactly the vector in black. So we built it out of little pieces. Okay, so that's all unit vector notation is. You're stacking little vectors together. What's that? Yeah, just stacking them up. And of course, you could do like a half a j if you needed to. Like you can use a quarter j. You can use whatever size j you need, 2.5, things like that. All right, so I think this will be the last thing we do. So I want to look at the same things we've done for vectors so far: adding, subtracting, scaling. But this time I don't want to draw any. I just want to use numbers to do it all. So to do this, or to explain it, I'm going to use two vectors, v and w. There's vectors v and w. Each vector would have a horizontal and a vertical component. When we do an actual problem, they will be numbers like that. Okay. But to represent them generically, I'm just going to say x1, y1, x2, and y2. I don't know what the numbers are. And alpha is a scalar. So remember, that's a number you put in front of a vector to make it longer, shorter, or change direction. All right. Now, let's say we want to add two vectors together. The old way. Take the first vector, take the second vector, connect them like that, and then draw the diagonal. We can do that same thing without adding, or without drawing. All you have to do if you want to add two vectors together is take the two numbers that represent horizontal and then add them up. Take the two numbers that represent the vertical and add those up. And that's all you have to do. So you just add them up. What do you think the difference in the formula would be if I want to subtract the two vectors?
X1 minus X2,
Yeah.
and then same thing for Y.
Yep. So now instead of doing that stuff we had to do visually where you flip the second vector around and then add it to do subtraction, we don't have to do any of that. You just take the first horizontal component and subtract the second one. Take the first vertical component, subtract the second one. Now with subtraction, does the order you subtract them in make a difference?
Yes.
Yes. Addition, no. But subtraction, you have to do it in the order they tell you. If it was w minus v, that's a different question. Okay. What do you call that when you put a number in front of a vector?
Theta. Alpha.
Yeah, so the Greek letter there, that is an alpha.
Multiply.
Scalar.
Scalar. Yep, that's a scalar. Scaling is also pretty straightforward. If we were doing it the old way, like let's say it was 5v, you'd have to take 5 v's and stack them all up. This way, you just take whatever number is in front of your vector and you multiply it to each component. So it's kind of like a distributed primitive. That's what scaling is. Multiply your scalar to each component.
Wouldn't you ever do that for x2 and y2? I mean, yeah, x2 and y2 as well.
Well, if you were going to scale w, but in this case I'm scaling v.
Oh,
Yeah, scaling is not an operation when you need two
yeah,
vectors.
that's fine.
Adding and subtracting is. But yeah, w wasn't part of that.
Sorry about that.
Yeah, you're good. And what about this? Double bars around a vector. What does that mean?
Magnitude.
It means magnitude. And if this is your vector, and this is x1, and this is y1, the horizontal and the vertical, what theorem did we say you can use?
Pythagorean.
Yep. So what is Pythagorean theorem?
Magnitude.
Like if you did it with
Oh.
those, how would you write it?
X squared plus y squared equals c squared.
Can you say it again with those letters?
B x1 squared
Mhm.
plus y1 squared plus v squared equals v squared.
Equals v squared. And now the goal here is to find the magnitude. So how would you get rid of this square?
Square root.
Yeah, if you took the square root, you would get rid of that. And there's the formula for the magnitude. It's the square root of x1 squared plus y1 squared. There you go. So we'll try an example of each of those, and then that'll be it for today. Everyone have the formula? All right, so here's our two vectors. I've written them both in the unit vector notation and the algebraic notation. Usually you don't see it written twice like that, but I wrote it twice. Okay, first thing I want to do is v plus w. Okay, no sketch, just numbers. So if I add v and w together, what would my new horizontal component be? And let's write it as a unit vector first, and then we'll do it that way.
It'll be 5i.
So 5i. Okay. And what about the vertical component?
Negative 1i.
Say it again.
Negative 1j.
Yeah, you could put negative 1j, or you could just put negative j. That's fine. Or if you wrote it this way, what would be the two numbers?
Negative 1.
Yeah, now you have to put the negative 1. If you don't, there's nothing there. Yeah, and that's how you add the two vectors together. All right, let's subtract. So the old way, you'd have to take w, flip it around, and then put it on the end of v. We're not drawing it now. We're just going to subtract it. What would be my horizontal component? And let's do it with the i's and j's first.
Negative 1i.
Negative 1i. Yep. And the w and the vertical component?
Plus 7j.
Yep. It's going to be 3j minus 4j. So plus 7j. And using the other notation we learned,
Negative 1,7.
negative 1,7. Perfect. Okay, so it's adding, subtracting, scaling. Okay, old way, you would take 3 v's and stack them all up. Now we're just going to take the 3 and distribute it to each number, each component.
6i.
So 6i,
J,
and then what would come after it?
9.
Something before that.
Oh.
Yeah. So 6i plus 9j, or the other notation, 6, comma 9. You don't have to write each answer in both ways. Okay, I'm just showing you which one ever the book asked for, then just go with it. All right, and last problem. What's it asking for here?
Magnitude.
Yep, magnitude of v. So we're not using w at all. We don't need it. Okay, when I want to find the magnitude, what's the first thing I write down? That for my formula.
Square root.
Yep, put the big square root of.
x1 squared.
Okay, what's x1?
2i. Or 2.
2. Just 2.
Straight up.
So there's x1 squared
Plus 3.
Square.
plus 3 squared.
4 plus 9.
And what theorem are we really using right here?
Pythagorean.
Yeah, it's the Pythagorean theorem. It's just this side's 2, this side's 3. So you're just using Pythagorean theorem. That's all. Okay, 2 squared
4.
and 3 squared.
13.
And if they don't ask for a decimal, you can just leave it as the square root of 13. Otherwise, if they do, you could just type in square root of 13 and get the decimal. Any questions on that? Okay, so I'm going to have to tweak the homework a little bit because we kind of in the middle of a section, which is good. And then hopefully I think we'll be able to wrap this all up in 3 days instead of 4.
Nice.
Let me just find homework. And let me adjust that. Okay, so 25 to 40. Oh, yeah, I need to. Okay, so homework tonight. Again, that's not the one that we're doing right now. It's page 344. 1, 3, 7 to 17 is odd. And then 27, 33, 34, 39, and 40.